Before we start talking about the pH scale, it's important to realize that water has the ability to chemically react with itself. At room temperature, two water molecules can actually bump into each other and cause a transfer of protons. One of the water molecules acts as though it is a Bronsted-Lowry acid, and the other one acts like it's the base. The one that acted like it was the acid has lost one of its protons and forms OH-1, and the other water molecule that gained the hydrogen ion becomes H3O+. We'll talk about what this double-sided arrow means here and this expression down here means as well in one moment, but let's take a closer look at the Lewis structures of water to see what's going on. When water reacts with itself, the hydronium ion forms from one of those water molecules losing one of its H atoms, which then turns into an ion. It hops onto the other water molecule and it forms H3O with a positive 1 charge to account for that extra proton that it picked up. The water molecule that lost its H, however, is going to form the hydroxide anion because it's lost a positive charge. So these two things can form in water at room temperature, and they do, and this is actually what the pH scale measures. It measures how much of this thing here that I'm circling in red, the hydronium ion, is actually in solution. This chemical equation has a double-sided arrow because it's representing a state called equilibrium. Equilibrium means that the rate of the forward process is the same as the reverse process as well. This reaction happens at room temperature in water, and the expression down here is called an equilibrium expression. It has a constant value, 1 times 10 to the negative 14th, and that constant number is equal to the concentration of H3O plus times the concentration of OH minus. It just so happens that at 25 degrees Celsius, the concentration of hydronium and hydroxide is equal to 1 times 10 to the negative 7th molar, which is really small, but I want you to focus on that exponent of 10, that negative 7. That's why water has a pH of 7 at room temperature. There's an equation that we use to represent the pH of any solution that has water in it. And that equation is that pH, which actually symbolizes parts hydrogen. That's where that term comes from. The pH scale is a logarithmic scale. Now, a logarithmic scale is a scale that represents the exponents of numbers. And sometimes logarithmic scales, like the Richter scale that's used for measuring earthquakes, are best represented as powers of another number. In this case, we're looking at what power of 10 in the concentration the pH is representing. We take the negative log base 10, which there's a function on our calculator which will do this math for us, of the concentration of hydronium ions at the given set of conditions. And this is the equation that we use to mathematically determine what pH is. When we take a look at this expression, we can see that pH is always going to be the log base 10 of that concentration, but we take the opposite of it. When I look at the pH of pure water, right, we said the concentration of H3O plus is exactly 1 times 10 to the negative 7th. Well, if I take the log base 10 of that number, I get negative 7. And if I take the opposite then of that number, I get positive 7. And that's why water has a pH of 7. Something very important about the pH scale. Because it's a log base 10 scale, for every spot that you move on the pH scale, things become acidic or basic by a factor of 10. For instance, if I was comparing something that had a pH of 6 to water, I've moved one spot on the pH scale, which means that this substance is 10 times more acidic than water is. Alkalinity, or basicity, the degree to which something is a base, also scales up by that factor. So if I'm comparing two things that have different pHs, I have something that's at a pH of 12 and something else that's at a pH of 14. Since I know that this substance that's at a pH of 14 is 2 spots higher on the pH scale, this substance would have to be 100 times more basic than this substance that is at pH 12. So let's take a look at this quick concept check. Vinegar has a pH of approximately 2.0. If the pH of milk is approximately 6.0, how many times more acidic is vinegar than milk? I'll give you a few seconds here to work this out yourself. You can pause the video and we're going to go over the solution together. If I take a look at this, I can see that the difference between 6 and 2 is 4. So to figure out how many times more acidic it is, I simply go by a factor of 10 for each spot that I move. So 10, 100, 1,000, 10,000. I can also take 10 and take it to the fourth power to get my answer that it's 10,000 times more acidic than milk. This is the pH scale. Typically, acids are represented by the color red, bases are represented by the color blue. You can see that the reason why the pH scale is so useful is it goes by tens in terms of acidity and alkalinity. One thing to note is that when something is very, very acidic and it has a very low pH, the concentration of H3O plus gets really big, but the concentration of OH minus gets really small. When something has a very high pH, like 14 or 15, the concentration of H3O plus drops to almost 0, but the concentration of OH minus gets bigger. And notice how at pH 7, the concentration of H3O plus is exactly the same as OH minus. So the two things that are in water, H3O plus and OH minus, are both inversely proportional to each other. As one goes up, the other one has to go down. So there's an inversely proportional relationship between the concentration of H3O plus and the concentration of OH minus because the two numbers need to always multiply to give us this constant for Kw, 1 times 10 to the negative 14th. One other fact about strong acids and the pH scale. Since monoprotic, which means one hydrogen, acids are strong electrolytes, we can assume that the concentration of H3O plus is going to be exactly the same as the concentration of the original strong acid. So if nitric acid fully dissolves, it's going to split into equal parts H plus and NO3 minus 1. That H plus, or that proton, is going to be immediately picked up by a water molecule, thus making the concentration of H3O plus exactly the same as the strong acid that originally dissolved. When I'm calculating pH, I'm going to let my calculator do most of the work for me. So to calculate the pH of a solution where I know the concentration of H3O plus is 3.7 times 10 to the negative fourth molar, I simply just use the negative log base 10 function of whatever my concentration is, which is 3.7 times 10 to the negative fourth, and my pH comes out to be 3.43 if I type that in correctly into my calculator. I can also do the same thing if I know the concentration of a strong acid. I'm assuming that the concentration of H3O plus is the same as the original concentration of the acid. So therefore I take the negative log base 10 of what my original concentration is, and that comes out to be 1.82, which makes sense because this is a strong acid, and I would expect a strong acid to have a very low pH. Now there's another way that we can express this equation if we know the pH, but we don't know the concentration of H3O plus. We can rearrange this equation by dividing both sides by -1, and then to get rid of a log base 10 in math, we have to take 10 to the power of both sides, which will essentially undo our logarithm on this side of the equation. If I take 10 to this side of the equation, 10 to the negative pH, 10 to the log base 10 cancels out mathematically, and I'm left with this new expression which says 10 to the negative pH is equal to the concentration of H3O plus in solution. We can use this to go the reverse way if we know the pH of a solution. So if a solution has a pH of 2.14, what's the concentration of H3O plus? Well, here's my pH equation. The alternate way of expressing that equation is 10 to the negative pH is equal to the concentration of H3O plus. So all I have to do is take 10 to the negative, or the opposite, 2.14 power, and that will give me my final answer, which is 7.2 times 10 to the negative third molar. Here's two practice problems for you to try to use those two different equations that we use to calculate pH, or to calculate the concentration of hydronium. Try these two problems, pause the video, and we'll go over the answers here in a moment after you hit play. Since I know that HCl is a strong acid, I can assume that the concentration of the strong acid is the same as H3O plus. pH equals the negative log base 10 of 0.5, which comes out to be a pH of 0.30, which is a very low pH for a strong acid. To go the reverse way in number 2, if I want to find the concentration of H3O plus, I take 10 to the negative power of the pH, which is 5.89, and that comes out to be 1.3 times 10 to the negative 6th molar. This concludes our discussion of the pH scale. We'll talk about another expression that can be used, pOH, in our next lesson.